Hi everybody, so today we're going to talk about integrated rate laws. And so what we've seen so far for kinetics have been differential rate laws, where we have looked at a chart to figure out how the concentration of reactants can affect the formation of products or the disappearance of other reactants, and we solve for something called the rate law. And this is good when you have initial rates and you want to find out how the concentration affects the speed of the reaction. But what if we want to measure other things about a reaction? What if we want to figure out, well, how much of, A is left after 5 minutes, or what's the half-life of the reaction? Or, how much time does it take for there to be, zero point 0.2 molar left? And for that, we need to do the integrated rate laws. Each order has a different integrated rate law. And so the main ones that you need to know for this course are what happens when I integrate a first-order reaction, a second-order reaction, and a zero-order reaction. Well, if we look at the graphs here, it helps you to understand what happens and how to integrate this. So if you look on the left, this graph shows you, if I highlight here the axes, the pressure of this concentration of methyl nitrile and its disappearance over time. And what you'll notice is that the graph is curved. It has a nonlinear relationship. The rate slows down over time. And in order to find the rate at a particular time, we would need to take the slope tangent to a specific point. In order to find how much is left at a specific point in time, we would have to find that exact point on the graph. That's easier to do in some instances than others. If you're, at a specific, point where the two lines intersect, the two graph lines intersect, then it's easy to find out. But you'll notice that all these points are kind of out in the middle of nowhere. So integrating this allows us to make this graph into a straight line. And when we integrate first-order reactions, we get the following setup here. We have our original reaction, which looks like this. The change in concentration of A over the change in time is equal to the rate law, K times A to the first. If we integrate it, then we get the following equation. And I don't find this form of the equation that I just highlighted that useful. I love y equals mx plus b. And so that's what I do. I take this equation, and because it's logs, I can then subtract the logs when you divide them, and I can rearrange this. And this is the format that I love. Right here, I'm highlighting it. And I'll highlight it in a different color in red here just to make it clear. This shows you y equals mx plus b. And that's the format of this equation that I like so much. Y equals mx plus b. Y is the natural log of the concentration at any given time. M is the slope, negative k. X is time, plus the y-intercept is the natural log of the concentration of whatever reactant I'm talking about at time 0. This integrated rate law is so powerful for us to answer so many questions. Let me show you an example of what a question would look like for this and how we could do this. Let's say, for example, I were to give you this equation up here, and I were to give you this sample question here. I were to say to you, something like, how much CH3CN in torr, so we're doing pressure, is or remains, so remaining after 12,000 seconds. So if I try to do this with the curve line up here, I'd have to find where 12,000 seconds was, and it'd be difficult, and I'd have to then figure out how much of the times, how much of the pressure was left there. If I use the integrated one though over here, I have my ln of A at time 0. I don't know that, so that's my ln of x equals negative kt. So I would need to figure out what my k was first, so we're going to have negative k. My time is going to be 12,000 seconds, plus my ln of a at time 0, which is just plus 5. Now, I don't know what k is first, so I need to figure out k. So here's where I would pick a point that I think would work, best for me. And I would probably choose something like for 10,000 seconds, I would choose 4.5 for that. And I would first solve for k. Once I found k, then I could use that and I could plug that in to my equation and figure out what my value for x was. So this would require 2 steps. So let's go ahead and let's find k first. So we would have 4.5 equals negative k. The time we picked was 10,000 seconds, plus, and then ln of a at time 0 is 5. So if we do that, we get negative 0.5 when we subtract, divided by 10,000, so 0.5 divided by 10,000, and we get that k is equal to 0.0005. 0005. Now I can take this value and plug it in right here, 0.00005, and I could solve for my ln of x. So I times that by 12,000, then I 0.00005 times 12,000 plus 5, and I get 5.6. And so at this point they're asking me, that's not right. Sorry, it's not right. So we have 5 minus 0.6, so it would be 5 minus 0.6. So we have 4.4. So now we're going to have ln of x, and we'll do this in red just to highlight it. When I solve for this, I get ln of x equals 4.4. And now I need to figure out what that is by doing the anti-log of that. And so if I go e to the 4.4, I get 81.4, and that's my pressure. And so my pressure would be 81.4. So solving this problem, I first had to find k. Once I found k, I was able to plug it in, and I was able to solve for x and find out the pressure. This would be in torr in red here. So this is first order. What if I had second order? Well, second order, when I try and do the natural log of the concentration or the pressure, I don't get a straight line. When I do 1 over, I get a straight line. So now I have 1 over, and I can put this into y equals mx plus b as well. This time y is 1 over the concentration of whatever the reactant is. I'll put in NO2 since they have that. Equals, now the k is positive k times time plus the 1 over NO2 in this case, 1 over NO2 in this case, at time 0. This is at time t. And you can see that here, I have that written here in my y equals mx plus b format. Ask the same question, get the same answer, same type of thing. Then I could have something that was 0 order. 0 order, when I do this and I graph it, I get a straight line when I graph concentration versus time. And so my 0 order looks like this. So just to summarize this, if we are 0 order, if we are first order, if we are second order. 0 order rate is equal to k times a to the 0, so we leave it out. And the integrated is a at time t equals negative kt plus a at time 0. First order, we have rate equals k times a. And we would have our integrated rate law of natural log of a at time t equals negative kt plus natural log of a at time 0. Second order, we have rate equals k times a squared. And when we integrate this, we get 1 over a at time t equals positive kt plus 1 over a at time 0. Please know all three of these and know how they work. A lot of times what you're given is some data. So the first question they ask you is, determine if the concentration of N2O or the decomposition of N2O5 is first, second, or zero order, given the table below. Now there's two ways to do this. If you have a graphing calculator, you could plug it into your stat program and get a graph and see which one's linear. For those of us that don't have that, or if it's on a multiple choice, you don't have a calculator, you want to look for one where you're getting a straight line. A straight line of either negative slope if you're first or zero order, or if you are second order, you would have a slope with a positive line that's linear. So to have that, you need to have constant changes over time. The time is changing by 10 seconds between each interval if you look at it. Which one of these differences stays constant? Well, if we look at it, you can see that the ln changes, those remain constant. The only one that will give us a linear graph for the data is the natural log. The difference between each change in the natural log is about 0.3 usually. That change, that constant change, gives us a linear relationship. So I know that it's first order. Then they have a follow-up question. They say, well, it decomposes in a first order reaction. For this next type of question here, this is a different compound. And they say to you, they give you the rate constant, and then they tell you, what is the concentration after 0.01 seconds. So I know it's first order, so I'm going to have my natural log of my concentration of my substance, we'll just say x at time t, equals negative kt plus the natural log of x at time 0. Now I have to just plug in my values. Go ahead and try it. Plug them in, see how you do. Then they ask me what fraction has decomposed. So what's the percentage? So we're going to practice a whole bunch of these. Try this problem, see if you can solve for x, see what you get. And then we'll also try this tomorrow. We'll do a whole bunch of practice when we meet again in class, and you'll see how these work. We'll go through the reactions. But please take the time to know the 0, first, and second orders so that you know how to do these. All right, thanks so much for watching.